keeps popping up in the homework problems that I've assigned to you, and it's going to come up again in examples even today, is the dipole. And to a certain extent, it's just a matter of recognizing the form and saying, oh, that looks like a dipole. Let me find out what the dipole moment of that particular distribution is. And you could figure out what the dipole moment is by doing that, that integral over the charge that allows you to figure out what the moment is, right? Or you could say, hey, I know the potential looks like this. I just solved for it. And the dipole looks like that. And the coefficients on the two terms have to match up. And so that's the dipole moment. So all I'm going to write here is that the potential for a dipole is equal to the strength of the dipole moment, which for 2-point charges is just QD. 2-point charges of plus and minus Q separated by a distance D. That would be the dipole moment, okay? But you can solve for the dipole moment for any charge distribution. Okay, so that's it. Dipole moment over r squared cos theta. And you're going to encounter very frequently, as you did in the homework this time around, the situation where you work it all out and then you look at it and it's got a cos theta over r squared times something. That thing that multiplies it is the dipole moment of the problem, of the situation that you just solved for. And the examples that we've already worked on, which end up having the charge distribution in the field that ends up being equivalent to the dipole outside the charge, look like this. One of them was a metal in a constant field. And then corrections end up being made to that external constant field. Actually, the first thing that I should say is that I've applied this constant field. When I put the metal in there, let's say a metal sphere, what happens is that inside the metal, a charge distribution arises that cancels out the external field. And what that charge distribution gives rise to is a constant field that's equal and opposite to the external field. So the two cancel out, making 0 in the inside, right? And that charge distribution was sigma naught cosine theta. And the second problem that we looked at was actually a shell of charge. This is the one you just worked on, where the shell had a distribution of charge. Sigma is equal to sigma naught cosine theta. And what you confirmed, or if actually you were in the homework session, I gave you the long way around. I actually derived it, but I derived it incorrectly, deliberately. I gave you the idea how you would go through the full expansion solution for that charge distribution, where you write down the general solutions to Laplace's equations, then you write down the boundary conditions that apply. Potential at infinity is 0, potential at the center is 0. It's not allowed to blow up, but we actually know it's 0. And the Gauss's law tells us that the net flux of electric field through a little disk like that is
4 pi rho.
4 pi rho, 4 pi sigma, the charge density per unit area, right? So given those boundary conditions and the general forms of the expansions on the two sides, on the inside and on the outside, we found out for this problem here that the electric field inside is a constant, and the electric field on the outside is the field of a dipole. And you figured out what the strength of the dipole was, right? And shell. Yeah. The next problem that we're going to address, first I have to do some background, but the next example that we're going to address is the example of a dipole. Sorry. Is the example of a dielectric sphere of material placed in an external uniform electric field. And what we're going to find out when we solve this problem is that the dipole field, and I'll tell you what that means in a minute, that results from applying this external field and having this dielectric material is constant on the inside and is a dipole field on the outside. Right? So this example, this specific thing, just keeps coming back again and again. Whenever we put a sphere of something in an electric field, it ends up polarizing in a way so that it looks like a dipole. Okay? All right. So this class I'm going to talk about now theoretically, physics theory materials in electric fields. So we're going to be making some approximations, and I probably won't tell you where I'm making those approximations, but I'll try. So what happens to material when we put it in an electric field? And then what are the consequences as far as the influence that the presence of that material has on the electric field that was there originally? So we have a field, we put a dielectric in the field, what happens? Okay? Well, there are two things that we might worry about. And I'm going to draw a picture of an atom that is incorrect, but which is, let's say, the plausible thing that we do in all of the classical courses. I got positive nucleus and a cloud of electron wave function squared outside of positive. And so that's one possibility that I might have for an atom. Actually, all atoms are going to have something like that. Okay, a nucleus and a cloud. Right? Molecules could be different. Right? I could have a net positive charge on one of the atoms of the molecule and a net negative charge. And what I'm talking about is I've actually got positive and positive, but what's going to happen is that the electron cloud might spend more time over here than over there. Okay. So this molecule has a dipole moment. This one doesn't. Right? But no matter what, when I apply an electric field to this problem, what's going to happen, let's say I apply a field this way, is that the nucleus is going to get pulled a little bit that way, and the cloud is going to get pulled a little bit over that way, giving rise to a dipole moment. So now I've got a dipole moment that points like that. Initially, the atom didn't have a dipole moment. I applied an electric field. Now it does. Right? And similarly over here, I'm actually going to get polarization of the electrons. But more importantly, what's going to happen when I apply my electric field is that this net, if I drew it again like this, net plus minus like that, is going to rotate in the field, and I'm going to get that. And now I've oriented my dipole moment. So in gases without a net electric field, the atoms just sort of tumble about, and the gas as a whole has no dipole moment, has no net electric field over large distances, because the atoms are just randomly rotating with respect to one another. When I apply an electric field, the atoms tend to align in the field. They're still tumbling about quite a bit, but they align a little bit in the field. Yeah?
Would that mean that the gas couldn't have a net electric field or a net dipole field overall, since any of them do align? It'll force others around them to align the other direction?
Yes. Yes. And probably Professor Cornish could give you a proper statistical mechanical argument for why that has to be. But yes, there are rules that have to do with the way that atoms can align with one another. And yeah, you apply an electric field and you sort of end up aligning atoms to oppose the field that you have. Okay, so adding an electric field creates a dipole moment in the direction opposing the field. The direction of the plus minus charge opposes the field. There was a question somewhere.
Yeah. In the one with two positive charges around the electron cloud, why does the electron cloud spend more time on the right side? Is it because
Oh, they're not two equal positive charges.
Which one's larger?
One could be hydrogen and the other one could be oxygen. Okay, so if it's hydrogen and oxygen, I need two of those.
Okay,
but-
so they're unequal.
They're okay, totally unequal.
Okay, got it. Thanks.
Okay, so materials polarize. And for a single dipole, actually we already know what the potential looks like there. But I'll write it all out and include the angular dependence. Potential measured at a particular position is r minus r prime being the location of the dipole, right? Over r minus r prime, potential 5/2, right? But you say, but wait, that's a vector, that can't be.
R minus
I
R.
just put the
Prime in the bottom?
A prime is where the dipole is. R is where you're observing from. And this just takes care of the cosine theta that comes in with what I wrote over there. So now I could have a dipole pointing in any direction, and I can measure the potential at any point.
Is the second R in the bottom supposed to be an R prime?
Yes. Thank you. It is R prime in the printed notes, which you have not seen yet, because actually what I like to do is give the lecture, and then based upon comments that you make, correct it, and then host it.
Is that key to polarizability or the dipole moment?
That is the dipole moment, because this is the potential due to one dipole. Okay, so if I actually want the potential due to a whole bunch of dipoles, okay, then I'm just going to sum over all of the dipoles. That's O prime here.
Is that
I'm just going to integrate over all of them. So now I've got a bunch of dipoles all put, all over the place, right? And I can have any distribution that I like, right? That's true, but I'd like to try to put it in some form that makes it a little bit easier to interpret, so that when we look at a distribution of dipoles, or we look at a charge distribution, we can look at it and say, oh, that's like that, and that's like that, right? Where I'm going to go with this is a question of whether I've got dipoles distributed uniformly over space, or whether I've got dipoles which are distributed in such a way that I end up with a net charge on one side and a net charge on the other side of the space. Okay? So what I'm going to do next doesn't make sense until, no, until we do a few more steps. But I'm going to make an observation, which is that the gradient of the quantity r minus r prime. That's it. So that, I'm taking the gradient in primed coordinates, and there's my prime coordinate over there. If you work your way through that, then that is equal to r minus r prime divided by it's equal to that. Okay? So my that's true. That's for all of them. Yes, I'm sorry. I skipped, I lost a step here. This is still the dipole moment per dipole that we're adding up in here. What we actually want to do if we want to integrate over some volume is have some expression of the density of dipoles. Right? So I should have, I did want to rewrite this as same factor here. That's the density of dipoles, number density of dipoles, moment per dipole, dv prime. And over here, this should have been a sum over all of the dipoles. This is an integral over the dipoles. I changed it here to an integral over volume, right? Where this thing here is the density of dipoles. Okay, I'm going to go one more step then. I'm going to erase this first though. Density of dipoles is what that is. And now comes, Alex, I think you might have gotten ahead of me here. You asked about this. This step.
Is that supposed to be r minus r prime to the 5/2 in the bottom, or?
This is now the polarization of the material. It is the density of dipoles times the dipole moment of each of those dipoles. And the two dipoles don't have to be equal. What I can do now is just look at this and say, I've got a density of a certain type of dipole, those I add up, and I've got a density of a different type of dipole, then I add those in. So I really should put a sum over all the possible types of dipoles. But I'm just going to save myself some time and not write that out, Jake.
Are you sure that the expression, below, the second expression is right? It doesn't have the same units as the first one. I'm sorry, no it does. It's D.
Yeah, I switched the, yeah. The way I had left it a moment, yeah, actually what happened was I wrote this and then I looked back up and said, oops, I better change what I'm integrating over.
Okay.
All right, so yes, you caught me, but I caught myself before you caught me. All right, and that is not the principal line integral for those of you that complex variables. Sometimes that is.
Should that be over 5/2?
Yes.
Over the 5/2.
Yes. Okay, now I got this dot product in here. I can rewrite that integral that I had over there. And the potential looks like the integral of the dipole density, the polarization of the material, actually, which depends upon position. Gradient of And now I don't have to remember the 5 halves. Okay. Now what I'm going to do is integrate by parts. Integrate that by parts. But it won't be that bad. I'm not going to actually do the integral.
Are you just gonna look it up in your handy dandy shells?
No, I'm going to leave it in general form. And then rather than doing the integral, I'm just going to point to it and say, we'll call this that, and we'll call that the other thing. Rather than solving it, we'll give it a name. And then once we've given it a name, like a Bessel function, we no longer have to think about the fact that it's an infinite series. I'm pretty sure that there's, in some ancient and very intelligently thought out religion, there's something that has to do with giving something a name and having control over it after you've given it a name. Okay, that's the integral by parts. Just to remind you. I'm sorry I forgot the hands today, because they would be quite good right here. It's obvious. Yeah.
Do those all have 5 halves on them?
No,
Okay.
none of them have 5 halves. All of them are just the way they are.
And we love them just the same.
Yes. Okay. Hey, we learned about the divergence theorem. I have an integral of the divergence of something over a volume. All right? So that, I'm sorry I'm working backward on this board, but I'm not. That's,
You're working forwards and reverse.
yeah, okay. I'm sure I got that right. Dot dA minus, the other one remains the same. Yeah. Divergence E divided by r minus r prime dV prime. So now I've got a surface integral and a volume integral. And now we name it. Oops. Those are all primed derivatives there. We call, actually let's do it this way, P dot surface normal, so that's actually I'll write dA in a different way, n hat dA. I had promised myself I wasn't going to do that, just erase something and rewrite it in chalk. But that's small enough that you can probably fit it in. And if you haven't learned to write in pencil by now, then tough.
Then you fail.
V dot n, to the normal to the surface, is, I'm going to call that sigma P. All right? That's an effective surface charge due to the polarization of the material. And the way that you can think about it is that I've got some material here. I apply an external electric field. And then just like with the metal, what's going to happen? Well, no, not just like the metal. Let me just talk about dielectrics here. What's going to happen is that every single atom or molecule in here is going to polarize a little bit. So I end up with plus, minus, plus, minus, plus, minus. But then right next to it is a minus, plus, minus, plus, minus, plus, and so on, all the way across the material, right? But now they're oriented. So I end up with a net positive charge on this face and a net negative charge on that face. So applying the external electric field causes the atoms to polarize, so that I end up with a little bit of extra charge here, and a little bit of absence of extra charge over here on the other side, okay? So when we talk about that sigma sub p, that's charge density per unit area due to the polarization of the atoms in the material, and the fact there's an edge, and atoms can't leave the material. So I get a little bit of positive on one side, a little bit of negative on the other side. This charge, and in my written notes, I've got a different letter for this here, and I'm torn as to whether to switch it right now or not. I will. But this is sort of it's also a definition, and I don't know what symbol to use. I guess it's a definition. Sigma sub b, which in the textbooks, and I too will refer to it, is called the bound charge. That is that all that charge is on the material. You don't have any net charge on the material. You're moving it around a little bit. It can't leave. It's bound to the material. And usually the sum of all the bound charge is 0. In particular, the sum of the polarization resultant surface charge is 0. If you put something somewhere, you have to take it from somewhere else. Okay? And then I'll define the bound charge density and this is why I didn't like using sub b. This is the charge that's bound throughout the bulk of the material, so bulk density. And this is the bound charge that's sitting on the surface of the material. Okay, so surface density. So I don't like using B because you might think of bulk. This is surface, sigma is surface, rho is in the bulk of the material. Okay? So then the potential, just rewriting it in terms of these new words that we've used, new definitions that we've used, is sigma bulk over, oh, see, I said bulk. Sigma bound over the distance, integrated over the surface area on which the charge sits, plus the integral, I'll be explicit here, volume, rho bound bulk. Over the volume. Yes, Calvin?
Would that be a minus volume integral?
No. I
No.
didn't make a mistake there, because there's a minus sign here in the definition of the density. And that's to make this have the same form as the relationship between the electric field and the charge density. When you take when you work your way through and you start with the potential, you end up with a minus sign. Minus del squared is the charge density. So we want it to look similar. The only thing that's missing here actually is the 4 pi. And unfortunately it's missing from the way that we did this. We could have defined it with a 4 pi. And it will show up on the next page. Okay, for a uniform medium, something like this, where I've got this uniform bulk of material, it's just a constant material, I'm going to have no net charge inside the material. Okay? But if I had a problem where I had a whole bunch of little holes cut in this thing, then what would happen is I would get, actually I don't know exactly what I would get, but what would happen is I get a little bit of polarization at each of these surfaces. And then that row allows us to take into account the average polarization due to little holes in the material, for example. Or if I change the material, maybe I have, a chunk of material that's different from everything else here, then that bulk thing will take care of that. Basically, you use the bulk thing whenever the divisions of surface area that you're looking at are small enough that you can average